This item B, intrinsic geometry, exterior algebra in 3D. Could be 2, 3, 4 dimensional, you see, any dimension. Yeah, item B, part 2, manifold, attention, push forward and pullback. B, part 2, lecture 6, the adjoint operator. Now you use the adjoint operator in manifolds M and N. So let's consider the manifolds M and N. This is manifold M, manifold N. This is a point P. Attention now, this point P belongs to the manifold M. Then there's a function F, the map F. This map point P to point Q that belongs to the manifold N. So this is a push forward operator. This transfer map the vector xp to the vector, in this case, x, in this case, yq. xp map to yq. F maps point to point. This push forward maps vector to vector. Okay? That's a curve gamma n of lambda. That's a curve gamma m of lambda. There's a point P. Now, Q is this map F acting on P. So, YQ, you see, now there's a vector. This is a push forward operator, X on XP, and also another notation here is good to emphasize. This over here, you see exactly this one here. See this operator, this is a push forward. You see, that's an operator, is a vector, okay? YQ is a vector, and DFP XP is the same of the push forward operator here, okay? Those are vector. These are vector. XP is a vector and YQ is also a vector. Now, a very, very, very important property. This vector, okay, acting on a scalar function f, you see, this vector, these are the components of this vector, okay, and the space vector. And this partial xi is the basis of the space vector, acting on f. You see, we already derived this, showed this in previous lectures. Now, I can substitute this function f by a coordinate. As I emphasized before, coordinates are functions, you see? So this is xj, you see? This xp, xj. Now I substitute the vector xp by its components, okay, right here. But I can't take derivative on the manifold. That's as I emphasized in previous lectures. So this here is exactly identical to this. This belongs to the real, you see? So partial of uj respect to ui here is delta ji. Delta aj acts on xi here and leads to xj, which is a component. Attention now, vector acting on a function is a scalar. That's a very, very important result. You see? So this figure here is this one, okay, in more detail. See? This is my function f, this is a push forward, vector to vector. You see, this is a symbol over here, in this case. This is the same, attentional, as this one, see? As I pointed out over here. So this is a vector, okay? This is a vector. This is a push forward xp, leads to the vector yq. G is a function, okay? G is a function that belongs to n. But, attention now, the argument of a function is a scalar. That's why G acting on point Q, this is a scalar. You see, this is a scalar. That's a real number. Here comes the pullback. Pullback acts on a function, okay, or on a scalar, then transform, okay, and map to this case. You see, this G. Attention now, this here is a scalar, okay? F act on the scalar, okay? This belongs to the manifold M. Now I'm ready. Okay, I'll explain this, okay? I'll expand and explain each one of these. You see, this is pullback. This G, the function, belongs to N, but if I have a point, attention now, if I have a point over here, okay, then G, for instance, G of Q is a point. This is a scalar. It's easy. For instance, from calculus, you see, for instance, f xy is equal y squared plus y cubed. You see, f 1, 2 is equal 1 squared plus 2 cubed. This is 8 plus 1 is 9. So this here is a scalar. So when f acts on a point leads to a scalar. Exactly what I'm emphasizing here. You see, in this case, we have g of theta, this is a function. At a point is a scalar, exactly what I pointed out over there. So then, in this case, yq of g, this is the same, attention now, this is a push forward, okay? This is the same, push forward. Act on g, I'll show that this combination is a scalar. Look how easy, you see? This is a point Q. This over here is a point Q. DFP, you see? That's a, I'm sorry. This one here is this, okay? DFP is this. So act on G is easy because this is a vector YQ. Is yi partial of G with respect to yi. This is attention. Yi are the coordinates on the manifold N. That's important here. Likewise, as we did over here, is the same over there. You can't operate on and take a derivative on the manifold. So you'll substitute this by, for instance, partial of Vj respect to Vi. So instead of U, you see, I call V. So it's delta Ij, this Yj. It's important. Again, a vector acting on a function is a scalar. That's important issue. Then, just to clarify, you see, I just copied from here to there. Xp and the pullback of G belongs to the manifold M, a manifold. Yq and the function G belongs to N. I apply the adjoint operator over here. You see, that's an inner product. That's an inner product, okay? Exactly how I showed in a numerical example of adjoint operator. See, I just copy from here to here. I use the adjoint operator. Now, attention now, xp act in a function. That's a function, okay? Is a scalar. Attention now, you see? yq acting on g is also a scalar. You see, the results here are a scalar, g. Now, this case, the pullback of g, this is g composed with f, belongs to m. I repeat from here to here. So xp, instead of f asterisk g, I substitute by this composition over here is equal to the right-hand side. You see, this is the same as this. Okay? Next lecture, I will show an example just to clarify all this notation over here. Okay? It's a very simple example, but will help you. You see, when you see the next lecture, you come back to this lecture and you understand clear what's going on here. Okay, that's a fantastic the example that I will show. It's a very simple example. Okay, just for you to get a skill. Okay, just to play with this push forward and pull back.